This presentation includes the control solutions and compliance evaluation for normal operation of diode rectifier connected offshore wind power plants. My name is Ramon Blaso Gimenez, and I'm a professor with the Technical University of Valencia in Spain. We've been working for about 15 years on wind turbine grid forming control for both HVDC and HVAC integration. Diode rectifiers are a very cost-effective solution for the HVDC connection of offshore wind farms. There are several topologies that have been studied in the promotion project and have been shown to be technically viable. The obvious one is the point-to-point topology, but also it is possible to have a DRU-based link in parallel to a VSC HVDC link and also to a HVAC link, all of them connected on the HVAC side. It is also possible to connect the diode rectifier unit to existing interconnectors on the DC side and even to mesh HVDC grids. In most cases, the main problem is that grid forming wind turbine control is required for the operation of a diode rectifier HVDC connection. One of the main objectives of this work package was the validation of grid forming wind turbine controllers, which could be connected to DRU rectifiers. As you can see, the operational modes of the complete system include several synchronous AC modes and islanded modes, so the considered functional requirements have to be defined, taking into account all the possible operational modes. Not only that, we also have to consider all the fault responses to onshore and offshore symmetrical and asymmetrical faults, and also the possibility of providing ancillary services to the onshore grid. This is the system we have considered for a point-to-point link. We have a total of 3 400 megawatt wind farms connected to 3 diode rectifier units, which in turn are series connected on their DC side. The wind turbine auxiliaries are supplied by an umbilical HVAC cable, and the wind farm can operate as an island when the umbilical cable is not connected, and also synchronize to the onshore AC grid when the umbilical is connected. To start the whole system, what we do is first connect the umbilical cable to energize part of the offshore array cables. Then we connect some wind turbines and operate them in STATCOM mode, so now they can control the offshore AC grid voltage. Then all the rest of the array cables are energized and the remaining wind turbines are connected. At this point, the active power reference through the umbilical cable is set to 0, and now the wind turbines are supplying their own auxiliaries. Next, we connect the diode rectifier filters and the diode rectifier breakers, and the system is now in the standby for HVDC transmission. At this point, the wind turbines increase their voltage and the diode rectifier starts conducting and transmitting power. Next, the umbilical cable is disconnected, and finally the system reaches its normal operation mode. It is possible to disconnect the umbilical cable at an earlier stage, and that would lead to additional islanding modes of operation. The control for the complete system includes a top-level offshore wind farm offshore transmission system coordinator, which is in charge of changing the modes of operation of the complete system, and in turn controls or sends references to the onshore HVDC converter controller and the offshore wind farm controller, which in turn communicates to the individual wind turbine controllers. As an example, the considered wind turbine grid forming control is based on PVQ omega loops, does not include a PLL, and has internal current loops for protection purposes. It also has secondary control for umbilical synchronization and umbilical active power control. There are also other control strategies for DRU connected wind turbines with different characteristics. For example, with or without the use of PLLs, with using standard P omega QV troops, or a combination between different types of troops, with or without fast communications, with or without internal current loops, or requiring an angle synchronization between the different wind turbines. With the controller that we explained before, we are showing an example, which is one of the multiple tests that we have carried out for validating that particular controller. And in this case, we show the complete startup procedure from all the wind turbines being disconnected to the complete system delivering rated power through the HVDC link. Initially, we start with the synchronous AC mode with the umbilical cable supplying the offshore AC grid, or some strings of the offshore AC grid. Then we see some wind turbines being connected. When all of these wind turbines are connected and we have enough active power and reactive power to be able to supply the offshore AC grid, we switch on both the STATCOM mode in the wind turbines and the control of the power through the umbilical cable. And in this way, we see that the active power through the umbilical and the reactive power through the umbilical go basically to zero. After that, we keep connecting the rest of the wind turbines, and you can see that when we're connecting all the rest of the wind turbines, the voltage is controlled within the operational limits, and also the active and reactive power through the wind turbines are within the operational limits. Once all the wind turbines are connected, we move into HVDC standby mode, and then we start increasing the power going through the HVDC link to about 0.2 per unit. After that, we connect all the DRU filters. In each one of the filters, each one of the 3 filters has got 3 different blocks. Each one of the blocks are connected in sequence. And once all the filters are connected, then the active power that is being delivered by the wind farm is ramped up. And you see here that now the HVDC link is transmitting rated power. At this stage, what we do is just to disconnect the umbilical cable, and then we are in the normal diode rectifier mode of operation. As the main conclusions, we have developed together with all the partners in Work Package 3 the functional requirements, scenarios, and test cases for the detailed validation of DRU-capable grid-forming controllers. We have validated all these controllers in the different diode rectifier modes with different power levels and different number of strings connected. We have verified that the system operates correctly with a combination of grid-forming and grid-following wind power plants. And we have shown that standard grid-forming controllers can be used for DRU connection with relatively minor modifications. Finally, we put forward some recommendations for grid code changes for DRU operation. Thanks a lot for your attention, and I'll be happy to answer any questions you might have.
In this part, the performance of DRU-connected offshore wind power plants and the various faults are presented. My name is Li Zhu from University of Strathclyde in the UK. This shows the overview of the system layout. As you can see here, we have a 1200 megawatt offshore wind farm represented by 3 400 megawatt clusters. The offshore DRU consists of 3 units connected in series on the DC side and parallel on the AC side, each rated at 400 megawatt. The onshore converter is based on full-bridge MMC technology. So various faults are studied, including the onshore AC side fault F1, the DC cable fault F2, the internal DRU fault F3, and offshore faults at various locations F4 and F5. This shows an overview of the distributed grid-forming wind turbine control when connected through a DRU. It mainly contains AC voltage control, PLL-based frequency control, active power control, reactive power sharing control, and inner current control. To cater for the need for system operation and protection during various faults, the main performance requirements are to ensure safety of the equipment, to help detect and isolate faults, and also to support post-fault system recovery and restoration. We have done extensive simulation studies considering the different types of faults as previously described. Here we are going to show a few examples, starting with onshore AC faults. So a fault applied at 0.3 seconds and is cleared at 0.6 seconds. So when the fault occurs, the power transmission from the onshore MMC to the connected AC grid is reduced. As a consequence of that, DC overvoltage start appearing, as you can see here. The offshore wind turbines then enter AC voltage limiting mode. So the AC voltage offshore is limited to around 1.05 per unit as set up by the controller in the wind turbine. This in turn would limit the DC overvoltage to around 1.25 per unit, and the power transmitted through the DRU to onshore is automatically reduced to around 0.2 per unit in this example. When the faults are cleared at 0.6 seconds, the system is quickly restored and the full power transmission goes back to the pre-fault state within about 50 milliseconds after fault isolation. The second example we are going to see here is the system performance during offshore AC fault. So string 1 will experience a 3-phase AC fault at 0.5 seconds. Once the fault occurs, the offshore AC voltage rapidly reduced to almost zero. So the wind turbines enter current limiting mode. They are controlled to contribute 1.4 per unit of fault current to the network for fault detection and isolation. During the fault, the power transmission is temporarily interrupted. However, the DC voltage is maintained by the onshore MMC. Once the fault is cleared at 0.65 seconds, the offshore AC voltage rapidly recovers, and the wind turbine will go to a normal power generation mode. And the power transmission from offshore to onshore will recover very quickly. To conclude, system responses during various faults have been investigated for DRU-connected offshore wind farm systems, including onshore-offshore AC faults, internal DRU faults, and DC faults. The overall system performance during the faults are largely comparable to systems using MMC HVDC-based connections. Due to the AC voltage and current limiting capability, wind turbine converters can continue operating during the fault cases without significant overcurrent. By continuously providing fault current from wind turbine converters during faults, it enables convenient fault detection, for example, using offshore overcurrent protection relays.